So last time we looked at percentile score, which told us what percentage of the population we scored higher than, or were taller than, or richer than, or whatever. What percentage of the population falls below us, and what percentage of the population falls above us, and that tells us exactly where we are in the population. That's one way of looking at our position in the population. Another is to look at the z-score, which is going to tell us relative to the mean, relative to the center. Are we above or below, and how far above or below relative to how spread out the data is? Let me give you an example. Suppose the average of the population was 5. It doesn't matter what we're talking about. And you're at 6. Well, that's above the mean. Is it a lot above the mean or a little above the mean? It really depends on how spread out this population is. If the population is spread out from 0 to 10 with an average at 5, then 6 is only a little bit above the mean. It's above, but not by much. But if the population was spread out between 4 and 6 with an average of 5, then 6 is really far above the mean. 6 is all the way to the end of the population. Okay, so if the population's real spread out, then being this much above the mean might not be that important. But if the population's very compact, then being this far above the mean is important. The z-score is going to tell us this, how far above or below the mean we are with relation to how spread out the population is. So we're going to need our measure of center to know if we're above or below, and we're going to need our measure of spread to know how far above or below relative to that. This is where that standard deviation comes in. We talked about it before, but we haven't done anything with it until now. Let's look at a made-up population here. Let's say this is Smurfs or elves or whatever, it doesn't matter. I don't want to deal with real numbers at the moment. So we get some population. The average height, mu for average, Greek lowercase m, mu. Looks kind of like a U, but it's mu. The average of the population, the mean, is 34 inches, and the standard deviation, remember lowercase sigma, is 4 inches. So we've got a population that's centered at 34 and spread out with a standard deviation of 4, which really doesn't mean that much to us yet. It will before too very long. The z-score is going to tell us how many standard deviations above or below the mean we are. And that's really easy to calculate. All we have to do is take our height, the thing that we're looking at, x, right? The thing we're looking at is always x, minus mu, tells us how far above average we are, and then we'll divide by the standard deviation, and that will tell us how many standard deviations above or below the mean we are. So for example here, suppose we were 38 inches tall. If I want the z-score for that, I would take 38 minus 34, right, minus the mean, and then divide that by 4, and that would give me a z-score of 1. And I chose it because it would be easy. A z-score of 1. We're exactly 1 standard deviation above the mean. 4 inches above 34 would be 38. So z-score of 1 means we're 1 standard deviation above the mean. What if we were at 40? You can probably do it in your head. We want the z-score. That would be 40 minus 34 over 4. That's going to give us 1.5. 1.5 standard deviations above the mean. Okay, so we know that 40 is farther above the mean than 38 is. Of course, it's got a bigger z-score. What if we have somebody that's below the mean? What if we have somebody that's down at 30 inches? Well, let's go at 32. We do 32 minus 34 divided by 4, right? Subtract the mean, divide by the standard deviation. That's going to give us negative 0.5. A negative z-score says you are below average on whatever scale this is, and you're below by this many standard deviations. Okay? That's all z-score is. Very, very simple. If you are average, then your z-score would be 0, right? If you're 34 inches, then you're not above or below the mean. You're exactly at the mean, so your z would be 0. Okay? Very simple to calculate. It doesn't have a whole lot of meaning for us yet. It will in the next couple topics. We'll tie this together with the percentile score and we will be referring back to these for the entire rest of the semester. One more example. I'm going to use this one a lot because the mean and the standard deviation are nice, and it's an easy example to use and follow. The average IQ score for all people, by definition, is 100. If you have an IQ of 100, that means you are average. The standard deviation is 15. The test is created in order to have this standard deviation and this mean. And also, I'm a big believer that IQ scores are almost absolutely meaningless. They're a perfect indicator of how well you take IQ tests and not much of an indicator of anything else, but they're easy to understand and talk about, so I like to use them as an example. So suppose you have an IQ of 130. What's your z-score? Well, 130 minus the mean of 100 divided by 15 would be 2. So you are 2 full standard deviations above the mean. That's pretty good, depending on the thing you're measuring. If it's the amount of household debt you carry, you don't want to be that high above average. But it tells us we're 2 standard deviations above the mean, which we don't have a context for this yet, but we will see that 2 standard deviations above the mean is actually fairly high. Suppose you have an IQ of 70. Well, 70 minus 100 divided by 15 is going to give us -2. That would be 2 standard deviations below the mean, which is a significant number. If you know anything about educational psychology and the laws around education, you know that 130 is the IQ that is the breaking point between normal and gifted. And 70 is the breaking point between normal and mentally challenged. That's where the definition of mental retardation begins, at 70. So those are 2 very important IQs, at least in the education system. We will talk more about z-scores and percentiles next time.